Let's see theorem number 29. Very important theorem. Yes, and very easiest theorem. This theorem 29 is also called fundamental theorem of arithmetic or unique factorization theorem. Unique factorization theorem. Yes, the name itself says that unique factorization theorem means if you take any integer greater than 1, if you take any integer greater than 1 like 4, 5, 2, 3 up to infinite, yes, so you can write 2 as 2 into 1, yes, unique factorization. We can write 3 as 3 into 1, 4 as 2 into 2 into 1, 5 as 5 into 1. Means you can write each and every number in a product of prime factors. You can write 100 as what? 5 square into 2 square. Yes, means 5 into 5 into 2 into 2. Yes, like this. This theorem says that की आपण कोणताही नंबर जो आहे तो प्राईम फॅक्टर्समध्ये लिहू शकतो, प्रॉडक्ट ऑफ प्राईम फॅक्टर्समध्ये लिहू शकतो. कितीही मोठा नंबर असेल तरी सगळे हे जे नंबर येत आहे प्रॉडक्टमध्ये हे काय आहेत? प्राईम्स आहेत, एकही कॉम्पोजिट नाही आहेत. ओके, तर आपण असं लिहू शकतो दॅट दिस थिओरम इज कॉल्ड युनिक फॅक्टरायझेशन थिओरम. येस, सो स्टेटमेंट एव्हरी पॉझिटिव्ह integer a greater than 1 can be written uniquely as a product of primes apart from the order in which the factors occur, that is a is equal to p1 p2 up to pr, all pi are primes, all pi are primes. ओके, जसं की आपण 100ला कसं लिहू शकतो? 5 इंटू 5 इंटू 2 इंटू 2 और 5 इंटू 2 इंटू 5 इंटू 2 और 2 इंटू 2 इंटू 5 इंटू 5. सी, but order is different, factors are same. Yes, order is different but factors are same. Understood? So proof is very easy. Yes, write down proof. Let a greater than 1. Yes, given that they have given us what? A greater than 1. B any positive integer. Yes, if a is prime, then a जर सतत प्राईम असेल तर काय? प्रॉडक्ट ऑफ a इज इक्वल टू प्रॉडक्ट ऑफ वन टर्म. येस, इथे दाखवा 2 इज प्राईम, 3 इज प्राईम, 5 इज प्राईम. सो वी कॅन राईट 2, 3, 5 as 2 into 1, 3 into 1, 5 into 1. Yes, call this as equation number 1. This is equation number 1. Okay, hence equation 1 follows trivially. Yes, equation 1 follows trivially, and the theorem is proved, okay. But if A is not prime, ए दोनच नंबर असते, एक तर प्राईम नंबर नाही तर कंपोजिट नंबर. जर इफ ए इज नॉट प्राईम देन ए इज कंपोजिट नंबर. येस, ए इज composite number, okay. A is composite number. See, if A is composite number, then there exists an integer D such that D divides A and 1 is less than D is less than A. Yes, consider the set yes of all such positive divisors of A. जर A composite आहे तर we can write A as D into any number. Yes, so consider the set yes of all such positive divisors of A. Yes, so from above statement we can write S is non-empty. S is non-empty. Therefore apply well ordering principle. By the well ordering property, yes, by well ordering property, yes has the least element. S has the least element, say Pi, okay. Thus by definition of S, the Pi is the least positive divisor of A. Then P1 is prime. Yes, so this implies A is equal to P1 A1. 1 is less than A1 is less than A, okay. P1 is prime. If A1 is prime, above equation 1 and the theorem is proved. Yes, if we take A1 is prime, then our theorem is proved. Yes, but if A1 is not prime, yes, A1 is not prime, then repeating the earlier argument, for A we produce a least prime divisor P2, yes, of A1 such that A1 is equal to P2 A2. Yes, 1 is less than A2 is less than A1, and then A is equal to P1 P2 A2. where a2 is less than a1 and a2 is greater than 1. Okay, continuing this process, if a2 is prime, means we here apply method of contradiction to a small part. Okay, if a2 is prime, proof is completed. But again, by if we take a2 is not prime, yes, otherwise if a2 is not prime, then a2 is composite, so we can write a2 as a3 p3, a3 p3, yes, where p3 is prime number and a3 is less than a2 and p3 is prime. Yes, understood. Yes, then we can say that, see, then we can write a as a is equal to p1 p2 p3 a3, where a3 is less than a2. Continue above process. Yes, since we have this sequence is decreasing, yes, we have a decreasing sequence. A is greater than, a1 is greater than, greater than, not less than. A is greater than, a1 is greater than, a2 is greater than, a3 up to 1. The process terminates after a finite number. After a finite number, say r. Yes, say r. So we can write a is equal to p1 p2 up to pr. Okay, where each pi is prime. Okay, thus the prime factorization of a is achieved. Yes, thus the prime factorization of a achieved, means we can write a is equal to p1 into p2 into pr, means we can write any integer, in the product of primes, yes, within the order. Okay, now we have to prove that uniqueness of prime factorization. Uniqueness of prime factorization. Yes, युनिकनेस ऑफ प्राइम फॅक्टरायझेशन म्हणजे काय, की जसं की मी तुम्हाला सांगितलं 100ला आपण कसं लिहित आहोत 2 इंटू 2 इंटू 5 इंटू 5. ठीक आहे, याची ऑर्डर चेंज करू शकतो, मीन्स 5 इंटू 2 इंटू 5 इंटू 2 किंवा 2 इंटू 2 इंटू 5 हे असं लिहू शकतो आपण. येस, बट वी कॅन नॉट राईट 100 लाईक 3 इंटू समथिंग और 7 इंटू समथिंग. येस, तर हे असे नंबर चेंज होत नाही. जसे इथे 2 2 आणि 5 5 आहे, तसे इकडे 3 7 किंवा 11 वगैरे असं काहीही येणार नाही. सो युनिकनेस ऑफ प्राइम फॅक्टरायझेशन. ओके ओके, सो व्हेरी इझी. सो ऑलवेज गो बाय कॉन्ट्राडिक्शन. येस, if possible assume that a is factorized in 2 different way. yes, समजा आपण 2 डिफरंट वेजने फॅक्टराइज, समजा 100ला आपण 2 वेजने फॅक्टराइज करू शकतो. 100च्या वेळी आपण एक टेक अ जनरल नंबर a. yes, we can write a as p1 p2 up to pr, and also we can write a as q1 q2 up to qs. okay, here r is less than or equal to es. okay, and what we have to prove, that we have to show that p1 is equivalent to q1, p2 is equivalent to q2, yes, PR is equivalent to QS, where all PI and QK are primes. All these are prime numbers. Okay, all these are prime numbers. Yes, there will be without loss of generality, without loss of generality. Okay, if we consider P1 is less than or equal to P2 is less than or equal to up to less than or equal to PR, and in a similar manner Q1 is less than or equal to Q2 is less than or equal to up to less than or equal to QS. Okay, so this equation call as 1 and this equation call as second. Okay, now from equation 1 we can write P1 P2 up to PR is equal to Q1 Q2 up to QS. Okay, so this implies P1 divides Q1 Q2 up to QS. This implies what? P1 is equal to QI for some I, where 1 is less than or equal to I is less than. Yes, this we can write by theorem 28. What is theorem 28? We have already learned, if P and Q1 Q2 Qn are all primes and P divides Q1 Q2 Qn, then P is equal to Qi for some I where 1 is less than or equal to I is less than or equal to n. I have already taught you this theorem 28. Yes, read this theorem 28 or see the video on my channel, theorem number 28. Yes, so this implies what? P1 is greater than or equal to Qi by equation 2. Okay, similarly, yes, call this as equation number 3. Similarly, from equation 3, yes, what this equation 3 implies? Q1 divides P1 up to Pn and Q1 is equal to Pi for some